So you can have this type of hypothesis. Okay. So there are two ways you can do it. One is to use ANOVA, and the one is to use t-test. And after that, you also need to calculate the coefficient of determination, okay, which is a R squared. Okay. So here I put the R squared, but some textbook they put the BR squared. So the value is between 0. So you know the R value is between -1 and 1. Correct? Okay. So what is the possible value for R squared? So it's between 0 and 1. Okay. So what the coefficient of determination tell you? Okay. They do not tell you the strength of the relationship. No. Okay. Because of the strength of the relationship is shown in the regression coefficient, the slope. Correct? Okay. So what they tell you actually is the how much variance that explained by this model. Okay. If you still remember the example that we did in the Excel for the correlation, the example that we have data set A and B, you see it's a perfect line, right? And we calculate the R is equal to 1. Remember? So for R squared is equal to 1 also. Okay. So if you have some data sets look something like this. Okay. Because the correlation coefficient assume the linear model, correct? So it's quite straightforward. So if you calculate the R is cannot be 1. Okay. So you know how to calculate already. So the R maybe is something like 0.6. Okay. So if you calculate the R squared, then it will be 0.36. It's much smaller. So from the regression correlation point of view, you don't really put a line, so you not explain how much the variance explained by a model, just how strong of the relationship this one and this one, and test whether this relationship is significant or not significant. So this is for correlation. For regression, we always have a model, right? We calculate, then we have the model, correct? So it is possible that these two models is the same. Okay, maybe it's y equal to 3s plus 2. This one also y equal to 3s plus 2. It's possible, right? Because this is a best fit line for all the data is fall on the line. Even though this one is not all the data fall on the line, but there is still a best fit line. Okay? Correct, right? So there must be a measurement to show the difference. Okay? You know that this model is a better model for this data set because they're almost perfect. They explain all the variance. There's no error. This one is a best fit model, but it's not the good model actually, because you can see there are a lot of the unexplained variance. Okay, so there must be a measurement. So the measurement that they use is this one, R squared, which is coefficient of determination. So you know the value is between 0 and 1, right? For this one, all the points fall on the line, so it's a perfect model. There's no error. So that means that this model explains 100%. Okay, and this model explains only 36%. So if this model explains 36%, how many percent of the variance is not explained by this model? So you just take 100 minus the 36%, then you have 64%. So this is really not a good model. Okay? Okay, right? So you need to calculate the R squared. So as I said before, you need to test the significance of each of these parameters, right? Okay, so you can use an ANOVA test. We're going to discuss ANOVA in the next video. This is how it looks like. Okay, we do it later. Don't have to worry. Okay. So somehow, maybe I explain a bit. So you have the total sum of square. So you know the sum of square actually is a variance, right? Before you divide by degree of freedom. Okay. So actually this is all the variance. So this is all the variance. If you have if your data set consists of 1000 experiment unit, then you take each of the 1000 experiment unit minus the mean of the y and then square them. So this is all the variance. And then you have a regression sum of square. Okay, so the regression sum of square is all the expected y value minus the mean. Okay, then you have the residual sum of square, which is all the value minus the expected, the difference. Okay, but to do this is quite difficult. So if you have calculate this and this, you can just take a total minus the regression sum of square. Then what is remain is the residual. Those cannot be explained by the regression. Okay. So what I show here, this is just a shorthand formula. Okay. So what you need to do next, because you still have to standardize it somehow, right? Okay. So that's the reason why you have to divide by the degree of freedom. So this is degree of freedom actually. So for regression mean square, so this is a regression mean square, calculate mean square. So that means that you take this value, divide by the degree of freedom. Okay. So for the regression, simple linear regression, the degree of freedom for the regression mean square is always 1. And you also can calculate the residual mean square. So you just take this, okay, residual sum of square that you calculate from here, not from here, but from here, okay, divide by n minus 2. Okay. You get the residual mean square. After that, then you can calculate the f. Okay. So what you can do is just put the regression mean square divide by the residual mean square. Then you get the f value. Okay. But this is your calculated f value, so you have to refer to the f table. Okay. So in this case, you just like alpha 0, if your significant level set in 0.05. For f distribution, there is no one tail, two tail. Right? Okay. So what I need to just put the degree of freedom, because you have 2 degree of freedom, right? Okay. 1 and n minus 2. If your data set is 1000 point, then it's 998, 1000 minus 2. Okay. Then what is your f critical value? Okay. Then after that, just compare this f critical with the calculated f. If your calculated f is larger than the f critical, then you reject the null hypothesis. So that means that your regression coefficient is not equal to 0. So it's significant. Okay? So for the R square, what you can calculate, because R square is the total variance that explained, right? So it's just that take this, you can just take this, divide by the total variance, then you get the R square. So you can use the same data set that you used before in your correlation that you make in Excel to do this. Okay, then you can see some relationship between correlation and correlation and also regression. Even though there are some similarity in the calculation, in the concept, but the purpose is totally different. Okay, do not confuse and miss out. Okay, so I just go a little bit further. Okay, even though you have not learned the F-test, okay, but just from a conceptual point of view, and hopefully you can understand a bit. So for example, you have all these points, or this is the first one, first case scenario. Maybe not too perfect, maybe one is outside. Okay. You have the mean y, correct? They say that we put mean y. Okay. And to calculate the total sum of square, you just take all the y value minus the mean y. Okay, all this value minus the mean y. correct? Then you get the total variance of the, okay? So there must be a variation, because if there's no relationship, okay, then your mean, your total sum of square is very close to zero, very, very small. Okay, so forget about this one first, focus on this one. So after you get the total sum of square, then you can, next thing you want to calculate is the regression sum of square. Okay. So for regression sum of square is the difference between estimate and also the mean. Okay, so this is your estimate, right? This is your estimate, the value here, and different from the mean. So total sum of square minus regression sum of square, you get the residual sum of square, correct? So now you can see that the total sum of square is the same as a regression sum of square. Okay? If you take this value minus with the same value, you get a 0. 0. Okay? But it's impossible to 0, right? So this is why I put an extra point here. Okay? So now at least you have some variation. A little bit of the variation. Okay? This one. Okay? So for the mean, this one, there's a little bit of variation. Okay? Correct? And also this one, the blue color is from here. So there's a little bit of variation here. Okay? So that means that you have more total sum of square, correct? Okay? Minus regression sum of square. You get a very, very small residual sum of square. Very, very small. Okay? Very, very small. There's something. Okay? Then that means that the percentage that you explain is very small. Okay. So maybe we just move direct to the R square first, okay? Because you calculate the total sum of square and regression sum of square. Let's say this is one value, it's very large, okay? And this is also very large value. So the difference is very small, correct? Let's say this is 3.635, okay? For the total sum of square, okay? It's a little bit more, right? So regression sum of square is a little bit less, right? So maybe it's 3.621, okay? If you divide this value, you will get the value 0.99 something. Okay, because the R square is the coefficient of determination, so it shows how much the model explains the variance. How significant of this model? Okay, it's not the relationship; it's a model. How significant of this model? So the parameter in your simple linear regression, the most important model, the parameter is the regression coefficient. Okay, so now we go back here. So let's say we use the same value, 3.621 divide by 1, you will get 3.621, correct? Then we calculate the residual mean square. Residual mean square is what? Let's say the difference is 14. Okay, 14 divided by n minus 2. Okay, so let's say if our n is 10, just 10. Okay, we just put n is equal to 12, easy. Then 14 divided by 10. So 12 minus 2, 14 divided by 10. So it's 1.4. So after that, you just take this value, 3.621, okay, the regression mean square, this one, divide by 1.4, which is this one, the residual mean square. So it's this one, you calculate this one, f. Okay, so you get some f value, right? Maybe, I don't know, 1,000 something. Okay, 1,000 something. Okay, it's very large. It's very large as f value. If you look at the t table, there's no such big value, right? Okay. So that means that it's very likely you reject the null hypothesis, which you reject this one. So this one is significant. Of course, it's significant. Okay. So now maybe I give you a few minutes. You just think the opposite scenario. Use the same logic that I explained to you just now. Yeah.